I now want to explain the proof of Stokes' theorem. We're going to start with a special case where the surface S is a graph. So it's the graph of some function g of x and y over some domain D in the xy plane. And as we usually do with graphs, we'll give it the upward orientation. And f can be any differentiable vector field. We'll write it as PQR, and we need to show that the integral over C of f dot dr is the double integral over S of the curl f dot ds, where C is the boundary curve of S with its positive orientation like this. Okay, so this is fairly straightforward using Green's theorem and the chain rule. We just need to be careful in the calculation because there are a couple of tricky points. So let's see how this works as a review of Green's theorem and the chain rule. So let's first evaluate the right-hand side. So let's first evaluate the curl. So the curl of f is formally it's the determinative I, j, k, d by dx, d by dy, d by dz, pqr. So the first component is ry minus qz. The second component is pz minus rx. And the third component is qx minus py. Now, the surface has a natural parameterization as a graph, so it's parameterized by the domain D in the xy plane. So the parameterization of S, as we usually do for a graph, is r of xy equals x, comma y, comma g of xy, where x and y are in the domain. And the rx cross ry, which comes up in the surface integral, we've seen that that's minus gx, comma minus gy, comma 1. Okay, and so the double integral over S of curl f dot ds is the double integral over D of the curl of f dot this rx cross ry, which is minus gx, comma minus gy, comma 1, ga. So when we expand that out, this is the double integral over D of, so the first term is minus gx times ry minus qz, so I'll write that as gx times qz minus ry. The next term gives me gy times rx minus pz. Okay, so that's this times this. And then the third term is qx minus py. So this whole thing, dA. And I didn't write it down because it would take too much space, but it's key to remember that all of this stuff, or these things, sorry, the gx and gy are evaluated on D, but this stuff here, the q's, r's, and p's, these are all evaluated at the point x comma y comma g of xy in three-dimensional space. Okay, so that's what we get for the right-hand side of Stokes' theorem. And I can't do anything to simplify this further, so I'm just going to put a box around it and leave it alone. And now we're going to evaluate the left-hand side of Stokes' theorem and hopefully get the same thing. So what's the integral over C of f dot dr? Well, I need a parameterization of the curve C, so let's draw the picture again. So here's my domain D over the surface S with its curve C. Now let's look at the boundary of the domain D in the xy plane. Let's call that C0. So we can choose a parameterization of C0. So this will be, say, x of t, comma y of t, where t goes from a to b. And this gives us a parameterization of c. And this is a parameterization of C0 positively oriented. Then we get a parameterization of C, so for each point in C0, I just take the point in the graph which is above that. So that's x of t, comma y of t, comma g of x of t, comma y of t. And again, t goes from a to b. So we'll use this parameterization of C. So I get the integral from a to b of, well, I have PQR dot the derivative of this parameterization of C. So that's x prime, comma y prime, and then I need d dt, well, I need z prime, so this is z. And what's d by dt of it? Well, by the chain rule, this is gx times x prime plus gy times y prime dt. Okay, so this thing here, this is z prime, where z of t equals g of x of t, comma y of t. Okay, so if I expand this out, get the integral from a to b of px prime plus qy prime plus rgx x prime plus rgy y prime. Now, we can sort of turn this back into an integral over C0, where x prime dt turns into dx, and y prime dt turns into dy. So this is the integral over C0. I didn't mean to write a C0 there. I want the integral over C0 of, so the x prime terms give me p plus rgx dx, and then the y prime terms give me q plus rgy dy. And all this stuff is evaluated at this point, x of t, comma y of t, comma g of x of t, y of t. Okay, now I can use Green's theorem to rewrite this as the double integral over d of q plus rgy x minus p plus rgx y dA. Okay, so now I need to calculate the partial derivatives of these guys with respect to x and y. Now this is another use of the chain rule. It's a little bit tricky, so let me show you how this works. So the first one, q plus rgy x, is the partial derivative with respect to x. So that to use a chain rule carefully, I'm going to put in what everything depends on. So q is evaluated at the point x, comma y, comma g of xy. And r is evaluated at the point x, comma y, comma g of xy. And gy is evaluated at the point xy. Now I have to differentiate this with respect to x using the chain rule. So differentiating q here, so I get the derivative of q with respect to x times the derivative of x with respect to x, which is 1, plus qy times dy dx, which is 0. And then I get the derivative of q with respect to z times the derivative of g with respect to x. So I get qz gx. Okay, so that took care of this part. And then I have to differentiate r and multiply it by gy. So similarly, I get rx plus rzgx, and this is all times gy. And then by the product rule, I also get r times gyx. Alrighty, and then so this took care of this first part of the integral. Now let's do the other part. So that's going to be p plus rgx y. So this calculation is similar. So I basically just switch the roles of y and x, and then switch the roles of p and q. So this becomes py plus pz gy, and then here I have ry plus rz gy times gx, and then I have r gxy. Now, in the integral, I'm supposed to subtract this bottom line from the line above it. Let's see if anything cancels. So first of all, I have an rgyx and an rgxy. So I can cancel these using Clairaut's theorem. And then here I have an rzgxgy, and here I have an rzgy dx, so those are equal. So I can cancel those. And so this integral here becomes the double integral over d of what? So I have some stuff times gx. What do I have times gx? I have a qz minus an ry. So I have qz minus ry times gx. And then I have some stuff times gy. I have a rx minus pz. And then I have qx minus py. But there are only 6 terms left alive in here, so I've got them all. So that's what I get. All right, now we cross our fingers and go back to the previous page and see if this box expression agrees with the box expression on the previous page. Does it? Yes, it does. So that takes care of step 1. Whew, that was a little messy. All right, so the rest of the proof is simpler. So the step 2, it also works if S is a graph where you have, say, y is a function of x and z, or x is a function of y and z. So the calculation's similar, although if you're careful, you should do it and check. Okay? So it's a similar calculation. And step 3, so for a general surface, S, you divide it into simpler surfaces Si, each of which is a graph as above, as in step 1 or step 2. So that requires some justification, but you can prove that if the surface is smooth, then you can do it. Okay, so then the double integral over S of curl f dot ds I put an arrow over the del. Sometimes people do that. I was not doing that, but I did it. I just mean del here. Okay, so you can, as with any surface integral, you can add up the integrals over all the smaller surfaces. Now, each smaller surface has some boundary curve Ci. So let Ci be the boundary of Si with its positive orientation. So this is by Stokes' theorem for the simpler surfaces, it's the sum over I of the integral over Ci of f dot dr. But then this is the integral just over the boundary curve of C of S of f dot dr. And why is that? Well, so you have this big surface S, and this is divided into some smaller surfaces, so maybe this is S1, and this is S2, and this is S3, and so on. And each of these surfaces has its own boundary curve, which is supposed to be positively oriented. Now, where two of these surfaces have an edge between them, then there's part of the boundary curve of each of the two surfaces going along that edge. But these boundary curves go in opposite directions. They have opposite orientations. So, I mean, if you have the edge between two surfaces, then the positive orientation for one of the surfaces is opposite the positive orientation for the other surface. So everything in the interior cancels, and all you're left with are the parts of the curves of these surfaces that go along the boundary of the whole surface S. Okay, so this equality here holds because the interior boundary terms cancel in the sum. So that's the proof of Stokes' theorem.